Hello, my name is Swapneil Basutkar and my CWID is 503099904. And the topic that I'm trying to present here is from the paper, and the topic is analysis of real-time operating systems, file systems, built-in cameras from vehicles. So here we'll see how the built-in cameras of the various vehicles from various companies is used in the process of digital forensics. Let's move on. So the table of content is something like this. First, we have the abstract, introduction, related work, experimental environment, proposed method for DVRS file system. So here, the DVRS stands for Drive Video Recording System. So that's what DVRS stands for. And then we have results of file system analysis, case study, conclusion, and future works and references. Abstract. So daily used vehicles capture significant amount of information to embedded systems. And RTOS, which is real-time operating systems, dedicated file systems, was a challenge for digital forensics. This study focused on analyzing the dedicated file system of vehicles built-in camera. And the normal operation of the camera allows for various methods of video data acquisition. When the camera circuit is damaged, the only option is to extract the onboard memory. And reverse engineering was used in this paper to analyze the drive file in the system area. Multiple partitions stored in the analyzed memory contain log files and user setting files. Extracting the unallocated area of the video storage partition enabled the restoration of more video frames. We also see this method can be applied to analyze various RTOS and dedicated file systems in future research. The next is, now let's start with the introduction. So vehicles are becoming more electronic and software centric than it was, let's even say 10 years ago. With dashcam systems, navigation devices, GPS systems, autonomous driving features like Tesla, real-time operating systems, also the abbreviators RTOS, and dedicated file systems are used in vehicles for high responsiveness and compatibility with flash memory. Digital forensics works on vehicle requires targeting different real-time operating system environments for each manufacturer and model. So, so here the focus is on Hyundai, Kia, and Genesis vehicles. So we do reverse engineering is used to extract videos from damaged devices, and the results are compared with the manufacturer-provided file system drivers. Previous studies have explored various operating system, file systems, and video file structures in vehicle system, but not specifically in the real-time operating system. And that is the place where this paper is trying to focus. The adoption of RTOS in vehicle electronic control unit and ECUs is expected to increase. And the study highlights the need for further research into digital forensics in the context of vehicles, because it becomes very important in any of the crime investigations. The audio and the video coming from a vehicle which might be involved in the crime or any other is a very crucial evidence, and it's a very important part of digital forensics. So let's see some important and the related work that has been done before. So first thing is about dashcams. Dashcams are crucial in traffic accident analysis, like I said before, providing video evidence both inside and outside of the vehicles. Dashcams are evolving to include GPS data, lane keeping functions, and distance measurements from the vehicles in the front. That's what is happening with Tesla. Everything is in software, and dashcams help a lot. Traditionally, third-party companies used to manufacture as external dashcams, but vehicle manufacturers are producing internal dashcams now, and this is where it gets interesting. So if you check out the table 1, we have external dashcams here versus a built-in built-in dashcams. And the memory type, real-time guarantee, externally connected devices, reliability information, and the lifespan. So if you check each of this for external dash cams, the memory type is micro SD and SD card. If a built-in is onboard eMMC, we'll see what is this eMMC and thumb drive further. And then real-time guarantee is none for this. This is must guarantee. Externally connected devices is GPS antenna. I'm so sorry. And here it is AVN, stands for audio, video, and navigation, GPS antenna, various sensors. ECU stands for electronic control units. Externally connected devices, the reliability information, this is low. Independent operations, it's highly reliable. Lifespan, up to memory life, up to vehicle life. So we can clearly see why the built-in dash cams are so much more useful and make sense. Dash cams store video data in external memory using a file system method like FAT or customized format. The market is shifting towards internal dash cams integrating into driving assistant devices. Tesla vehicles record multiple channels of video data, including an internal channel to monitor the driver situation. Uh, the Hyundai, Kia, and Genesis, which are the three different car companies which are focused in this paper, vehicles launched after 2020 are equipped with built-in cams for front and rear view video recording. The eMMC memory of built-in dash cams store video data and can be accessed by USB or AP connection. The characteristics and forensics process differ between external and built-in dash cams. And the second one under the related work is RTOS and the dedicated file system, real-time operating system and the dedicated file system. So the built-in dash cams present challenge in system analysis due to its utilization of a different OS compared to traditional desktops, laptops, and mobile devices. RTOS are increasingly used in vehicles, electronic control units for scalability, security, and real-time performance. And they employ priority-based scheduling in the microkernel system, like in the operating systems. Vehicle ECUs use various RTOS and file systems, leading to increased diversity in relevant file systems. And the vehicle manufacturers are developing their own operating systems, such as Mercedes-Benz operating system, MW operating system 8, Volkswagen Group's VW.OS, and Hyundai CCOS. These are the few to give an example. They have created their own operating system. The introduction of new operating system and file system in a vehicle poses challenge for digital forensics analysis. This paper focuses on methods to analyze the dedicated file system using built-in dash cams, DVRS modules, and emphasize the needs to understand the file system analysis for future vehicle forensics. Next topic is file system for flash memory. So as we can see that vehicle dash cams commonly use FAT-based file system for sudden power off, SPO resilience. SPO events such as car accidents or low battery levels can affect the storage of video and audio data. So dedicated file system for dash cam video recording system, that is DVRS, have emerged to address the sudden power off issue. Flash memory-based DVRS file systems employ page unit storage, view leveling techniques, and eliminate directory entry. File fragmentation is a common problem in DVRS, impacting performance and memory efficiency. Techniques such as journaling, HFAT, partition storage, and ACPA, FECA are produced to mitigate the file fragmentation. An onboard flash memory used in built-in dash cams is challenging to replace, requiring dedicated file systems. Many existing forensics tools struggle to analyze the read partition file system using the built-in dash cams. Let's see, the next topic is experimental, subtopic is experimental environment for the DVRS, try video recording system. I'm so sorry. Hyundai, Kia, and Genesis have introduced built-in DVR systems in the vehicle with over 34 models released since 2019, Hyundai 2022. The DVRS is capable of real-time recording from front and rear cameras installed in the vehicle. So this is what is really important. And the DVRS is connected to AVN, allow user to control DVRS, playback videos, manage recordings. It has G-sensor functions. The built-in cameras consist of front and rear cameras as well as CAN communication. And the storage medium used in DVRS is an onboard embedded multimedia card, also called eMMC memory. So if you see this diagram, it is the overview of the uh, overall the DVRS architecture. So the input devices are front camera, rear camera, AVN systems, and the manual save button. AVN is like audio video navigation, and this and then there's the output device of AVN system, USB memory or Wi-Fi dongle. That's how the output is provided. And then there is a DVRS system which lies in between, so which has a processor, G sensor, embedded memory, eMMC, and USB port. So this is how the DVRS. This is what is the architecture of DVRS. So next we see the data acquisition method. Let's say something happens, and now how do you acquire the data? So basically, there are three methods to acquire the data from the eMMC. That is the focus eMMC in the DVR system. That is focus here. So the normal method involves extracting image data via USB port. When the vehicle is turned on normally, the desired video can be selected on the AVN system screen and the data can be transferred. This is fairly simple. And in cases where the vehicle is damaged and cannot be connected to the DVRS module or AVN system, and the emergency download method provided by the manufacturer can be used. So here we are using the emergency download method. This method allows data acquisition even without a normal power connection. This is something like which is really good. And then the next method is the chip-off method used when the DVRS board is damaged and the internal circuit is not functioning properly. In this method, the eMMC memory chip is physically separated from the board and the data is extracted from it. I'm sorry. So these are the three ways in which the data acquisition can happen. The normal mode of data extraction via USB allows selective extraction of files passed from the file system, obviously because we have a lot of control. And however, the file logs and unallocated spaces cannot be extracted using this method. The extraction of file logs and unallocated space is not possible using the emergency download method too. More detailed information and use cases are given in this paper. So I've just mentioned it because it was important. I've gone through it. And so this is the system, the method of extraction of files from the DVRS. So this particular thing is a DVRS system. It's like a motherboard. And then there's a USB port and this particular, I'm so sorry. And this particular thing is the eMMC. And then, so the data between eMMC and USB port is from the normal way, it goes to USB memory or Wi-Fi dongle. From emergency download, like we saw before, if there is no power and but still we want, it can be put into the USB memory. And the last way, which is a chip off, it is of the dump image. So the next one that we are seeing is the acquisition of data by the chip off method, which is our focus here. So here, what happens is desoldering the onboard eMMC memory. So this is what is the first step. In cases where the DVRS board is damaged and the emergency control protocol, download protocol is non-functional, the onboard eMMC memory needs to be desoldered from the board. And this is done at a 300 chip removal procedure. So then there is the coating removal to gain the necessary access of the memory chip. Then there's chip removal process where you use where you heat or where you blow the hot air at 300 degrees Celsius for approximately 180 seconds to detach the chip from the board. And data acquisition for chip of memory, suitable socket specifically designed for the type of memory used, which is eMMC here, is used to acquire binary data from the entire area of the chip of memory. And partition data and designated roles, the acquired data from eMMC chip memory consists of 56 partitions, and each partition serves a designated role. Proposed method for DVR is file system analysis. Most of the obtained partitions were not analyzed. So, and the video file carving frame by frame restoration was attempted for acquisition of image. So, in video file carving, most files are fragmented and cannot be restored. Due to restoration of frame by frame, also known as sequence parament set (SPS), picture parament set (PPS), the image data was recorded discontinuously because of file fragments. That's so obvious. And so for this proposed method, so the proposed method is manufacturer supplied file system package. Most partitions. So this is the table 3, and it's a list of major file systems in the DVRs. And like for Bluetooth, we have FAT16. For boot, for cache, for modem, we have FAT16. For recovery, Android boot image, and Y videos. This is the TFFS is where one of our other focus is. We'll see further in the slides. And this is the size in kilobytes for each of these file systems. All right. So there is a Tuxedo flash file system, the ASCII byte sequence TFFS. So here in the image, you can see the unknown file system is Tuxedo file image was found at the beginning of each partition, indicating the presence of a Tuxedo file system. So at the beginning of each partition, wherever a TFFS was present, so it was identified that it has a presence of Tuxedo file system. Mounting as Tuxedo file system, the memory was mounted using the command mount -TTFS, enabling partition parsing database folder. The database folder contained SQLite formatted DB files with information about files created when the DVR G sensors detected an impact. That's when the vehicle is in some sort of accident. System file folder, the system file folder sorted settings related to the DVR's devices, including DVR's control, into modified by user setting. Thumb folder, it contained JPEG files created into some folder, EBT, MAN, NOT, PAK, matching the number of files. So these points highlight the challenges in analyzing partitions. The discovery and utilization of the TFFS, the limitations of the system, and the acquisition of important folder containing database files, system files, and JPEG thumbnails related to the DVR's device. Like we saw before. And we have, sorry. So here you can see each partition has a TTFS signature. That's how in the starting here. So that's how we know that this is where the next partition is starting. So our reverse engineering method. So for the day, now this is where it gets interesting. And the reverse engineering method that is explained in this paper are divided into 4 steps. So the first one is identifying the file system. So till now we saw a couple of file systems, and now this is how we do it. We first identify the file systems, acquiring the file system management software, analyzing of the operation of the software, specifying the file system structure specification, right? So identifying the file system. So how do you do that? So magic number in file system. So file system is a magic number in the header of the volume to indicate the file system type. And then there is string identification. A string found at the beginning of volume is likely to be the name of the file system. Searching for keywords. By using the identification string as keyword, additional information about the file system can be obtained by searching the entire disk image. Then there is /etc fstav file in Unix-like operating systems. If a keyword exists in /etc/fstab file, it confirms the name of the file systems. Extracting information, copyright statements, and software information. Strings in the disk image can provide details about the manufacturer and versions information of the file system. Acquiring the file system management software. File system management software includes kernel drives, kernel drivers, formatting tools, error checking, correction programs, cross-analysis of software, and then you have a Unix-like operating system, and then acquiring software. ELF files can be obtained through keyword search and carving methods. An analysis of the operation of the software. So software is analyzed using assemblers like IDA Pro and Gateway and debuggers like GDB. EFL files, Unix-like file system drivers and packaged in EFL files with extension of .ko. Superblock structure, the sync_fc member function pointer in the s_op superblock population. So the sync fc is a pointer. And then you have TFFS analysis. The function TFFS write inode is called within the TFFS sync fs function, which writes metadata and file contents to the flash drive. Extracting file creation time. To analysis, the format and location of the file creation time is TFFS were identified. So the structure of the file, so the results of file system analysis. Now we'll see the results of file system analysis. So 5.1 is structure of the file system. The analyzed TFFS has similarity to the fact-based file system. The TFFS divides a volume into a boot sector, a backup boot sector, a cluster allocation map, and a region down as shown in the figure in the next slide. So here we see how the boot sector, the CAM region, entire information is segregated in the code. So this is a C program, a very low level language. So we have a struct volume here, and inside the struct, so struct is like a you can imagine it like a class in on OOPS. So you have struct volume, and then inside that you have various structs like boot sector, backup boot sector, CAM region, and root direct. So if you see the boot sector, it has a couple of variables, variable type arrays of the byte type and int32 type. And similarly here int16 and byte types. And then CAM region is a array of type uint32 CAM links, and the parameter it's like boot sector dot number of CAM entries. So let's see what is this each. So here the boot sector. So the first one, the struct here, struct boot sector. Volume information is recorded. The list of fields in the boot sector. So here's with all these parameters, the volume information is recorded, and the backup boot sector, which is here, not shown in the copy of the boot sector, is stored. It's just the copy. Third one is the CAM region. Like we saw, this is the CAM region. The illustrates array of CAM regions. These entries serve a similar purpose to the FAT entries. Each CAM entry indicated the allocation status of a specific cluster, typically 4 KB or 16 KB blocks within the data region. And then we have our data region. The data region consists of clusters storing the content of directories and files. And the possibility of file system unit recovery. File deletion in the file system driver marks CAM entries in unallocated spaces. The proposed method successfully restored a video file from the extracted unallocated spaces. If clustered chain consists of adjacent clusters, carving is highly effective and the file recovery rate can be high. And now we move on to the case study. The file system analysis was conducted on 2 DVRS models. One is of Hyundai Sonata, and another one is Kia K7. Sonata's damaged. So the proposed methodology was in this, which we just saw in this paper, was done on Hyundai Sonata and Kia K7. Sonata's damaged circuit board required the chip-off method, like we saw earlier, while K7 allowed both emergency download and the chip-off method. Works. Both model had eMMC memories with the same partitions. Like we saw, eMMC memories are separated by the TFFS each partition starts with a TFS, and the 9 partition had TFS written at their beginning, like I told. Reverse engineering method given in this paper extracted more files from TFS partition compared to K7's emergency download mode. And this is where it becomes very important. Certain partitions such as systems user data, Y data couldn't be extracted through the emergency download method, but they were extracted through TFS partition. The proposed method allowed additional analysis of user action, system logs, and thumbnail image in specific folder. So here, if you see the list of major file systems in the DVRS. So using the paper's method, the method that is defined in the paper on Sonata and the Kia K7, you can see the partition name as cache, persist, system, user data by backup, data by video, and the emergency, and using the emergency download. Using the emergency download, none of them, nothing was extracted. Just the Y video, 446, this is just a parameter. And if you see the method which is proposed in this paper, the persist, the system, the user data, Y app, or Y data. So here's a lot more of information. There's a hell lot of information compared to the emergency download, and this is what is the main goal of this paper. System log contain traces of user behaviors, including G-sensor detected events with speed and clearly varied position records. Unallocated areas in CAM region marked with deleted markers provided additional image frame reconstruction opportunities. The developed method demonstrated comparable file system analysis performance to manufacturer provided method. So these are the two important figures we see the number of recovered files. It's 100, 200, 300, 400. And then this is comparing numbers of recovered files in the Y video partition. So we are just taking one of the random partition of Y videos. And this is our method. It means that it is a method used in the paper that we are talking about. As you can see, the number of files recovered were fairly the same. Normal drive cache event, switch event. There was none in database, but this is where the significance difference is. In the system file, we see the method which is proposed here, proposed in this paper, would fetch few files, and for the thumb files, that is thumb images files, a lot more information was extracted, which could be used to do digital forensics in a much better way. And if you see the cars, comparing the cars of K7 and Sonata, the number of recovered frames, the method which is used is file system pairing plus unallocated frames. The number of frames, recovered frames, are much higher compared to the file system pairing. And that's it. And so the conclusion and the future works of this paper is the paper discusses the file system analysis methodology for real-time operating system RTOS in environments like vehicles. Embedded devices with dedicated file system pose challenges for data acquisition, analysis, and forensics investigation. Manufacturers offer limited methods for data acquisition, which may not be feasible if the device is damaged. Future plans include analyzing dedicated file system in various RT environments such as satellites, smart cars, and robot systems. And these are the couple of references which were directly taken from the paper, and there completes my presentation. Thank you so much and have a good day. Bye-bye.